Okay, so we talk about how caching works and how to look up when you have an address, right, on the previous Wednesday. And also we talk about how cache is organized into different cache blocks, different cache sets, and how can you extract the index bits and the tag bits. So the first thing we are going to do today is to go through some example. And right now, I would actually show you the exam from the previous semester that I had right here. So let me switch back the screen to my primary screen. So let me stop sharing quickly and then share again here. All right, so can you see my screen with the box that said caching benefits? Okay, cool. This is actually a part of your in-class exercise today. Today, you're going to finish this first question. And the second question here that says caching basic, right? So right now, we are going to go through this question 2A. Question one would be some of the stuff from question one would be what we'll cover today. So right now, let's go through this question. Assuming that we have a 32-bit byte server process with a processor, actually typo, my bad, with a single level cache. And the cache is 16-way set associated with 16 cache set. Each cache block is 32 bytes. What's the total size of my cache? Can anyone want to attempt this question? Please go through step by step so that your friends can understand what you're trying to do. And I'll help basically. All right, so I know that a cache block is 32 bytes, right? I know that there are 16 cache steps. I know that there are 16 ways. So what do I do here to get the total cache size? See if I can draw. I have 32 bytes. I have 16 sets. And then I have 16 ways. Right? And this is way too thick. Oh. What do I do here from these three different numbers? Exactly, multiply them all. Can you explain to your friends why? Draw. You have this, right? This is number of way. This is number of set. This is number of my cache block. Okay. Think of it as this is like calculate the area of this. Each block here is 32 bytes. There are 16 blocks from the top to the bottom, and also 16 blocks from left to right. Why is that the case? From left to right, think of it as the number of ways. Number of ways is associativity, right? It means that I have 16 boxes because I have 16 ways. From top to bottom, I also have 16 boxes because I have 16 cache set. So at the end of the day, you can just multiply these three numbers together and you get the cache size. And that equals to what? So that's 2 to the 5, right? Multiplied by 2 to the 4, multiplied by 2 to the 4. This is actually simpler because you can add 2 to the 5 plus 4 plus 4, right? What is that? What is 2 to the 5 plus 4 plus 4? What is 8 plus 5? 13, right? So that's 2 to the 13. How big? Oops. How big is 2 to the 13? 2 to the 13 is actually 2 to the 10, right? multiplied by 2 to the 3. That's 8 multiplied by 1024. You see how I did a lot of like power tricks that would get you easily 8 times 1024. In the exam, you can leave the answer like this. It's fine. I can do the multiplication, and I believe you can go to the calculator and do the multiplication. Make sure at least your final answer is at least one single number. So 2 to the something, that's fine. The question is likely to be a take-home exam anyway, so I would leave it to you to do the calculation. But yeah, these are the answer. 2 to the 13. Okay. So given the same assumption, what is my set ID? The index bits for this address. How can I find that? So I have this address broken down into how many regions? 3, right? This is tag. This is index. And this is byte in block. If I have a 32-bit machine, how many bits do I need here for the byte in block? 32-bit machine. 32-bit machine byte address. It means that I need to be able to access my address should be able to access each individual byte. Yep. So one of your friends answered me privately that it's log 2 of 32. That is correct. So you need 5 bits, right? Which is basically log 2 of n, where n is number of unique address, right? Number of unique address that I need to be able to access. All right. Now, I know that there are 16 set. So how many bytes, how many bits do I need for the index bits? Basically, I just need enough bit to be able to differentiate between set 0, set 1, set 2, set 3, set 4 to set 15, right? So the index bit is log 2 of what? Index bit need to differentiate between all the sets. How many sets do we have? 16, right? You have 16 sets. So you put the number 16 here, that is 4 bits. How many tag bits do I have here? It's 32 byte addressable machine. It means my address is 32 bits long. If my address is 32 bit long, it means that I have 32 minus 9 bits left, right? So the tag bit is 32 minus 9, that's 23 bits, right? Okay. Can someone tell me what is the index bits from this address? From the address a bad beef? All right. So over here, the easiest way is go from right to left, right? The rightmost, what letter is that? F, right? This letter. What is F? It's 1111, right? Then you go to the next letter. That's E. What is E? 1110, right? Then 1110 because you have another E. What is B? B is basically 11, right? 11 is 8 plus 3. So 8 plus 3 is 1011. This is the byte in block, right? You don't even need to convert the whole address, but by this point, you know that these would be the set bit, right? Set index bits. So that is what is 111 in binary. That what is that converted to? 7, right? So you are looking at set 7. So the answer here is 7. The set ID is set 7. Any question here? All right. So if you have more questions, this whole thing is your in-class exercise for this class. So you can talk about this toward the end of this lecture when we are talking about the in-class exercise, or after this class during the office hour. So hopefully these would be a good exercise for all of you here to go through and get things like, okay, how can I identify the set bit? How can I identify the tag bits? How can I break my address into different bits? Okay. Is final going to be similar to this? Yes. It will be some form of this kind of question. This is me telling you how can I create a cash exam based on what we learned. Another thing I can do is I can write a program. I can write a program that do some loop, and then I can ask you what is the cache hit rate. I'll have multiple questions so that you can work from step 1 to step 2 to step 3, giving you hints along the way on how to do that. We will actually do a practice for that type of question next week. I mean, not next week, next lecture. The benefit of being able to do these kind of thing is when you actually write the program on your own, you now know how to write a program to maximize cache hits, which is what we'll ask you to do for assignment 4. All right, so yes, final will be something similar to this. Hopefully these in-class exercise give you some clue on how to solve this problem, and also the next in-class exercise hopefully would give you some clue on how to write a program to be more cache friendly. All right. Okay, so we talk about cache lookup, right? I have an address. I need to figure out whether my data is in the cache or not. Now we're going to talk about 2 more things: insertion and eviction. Why do I have to insert data into the cache, and why do I have to kick something out of my cache? Anyone want to guess why do I have to kick data out of my cache? Yep. First of all, data somehow it's not being used anymore, right? You're done using that data, and it takes up space. So both answers are correct. The both answers are totally legit, and that is actually the fundamental concept behind how can me as a hardware designer go and design a cache. I know that some data is not used anymore, right? And sometimes it takes up space. So let's talk about the first thing. How do I insert and replace the data? And let's start with the easiest one, direct map cache. What is a direct map cache? And can anyone recall from last week on Wednesday? What is a direct map cache? This is a special situation where we have how many ways? One way, right? Each cache set mapped to one block. There's only one cache block inside one cache set. So how do I insert or replace that data? Basically, if I have incoming access to set 0, what do I do? Anyone want to guess what do I do here? I have the old data inside the cache set, and I have a new incoming data that I am accessing. So what is the obvious option? I have the old thing and I have a new thing coming in. Yep, replace it. Kick the old thing out because you thought maybe it's not going to be used anymore. And hopefully the new thing that comes in is going to be used again, right? For set associative cache, where you have more than one way, it means that now these old items, let's say it's a four-way cache, it means there are four old things. There are four old things here, right? So you have something like this, right? So this is the set 0, cache block 1, cache block 2, cache block 3, and cache block 4. And I have incoming cache block 5 that say, hey, I want to replace one of these blocks here. What does this mean? It means that, okay, now we have a choice, right? We can pick cache block 1 or cache block 2, cache block 3 or cache block 4, one of this. And it depends on the policy we have. These are the key issues that we need to be able to figure out, right? Basically, where do I insert into the cache? If I have data access to my cache, do I promote them? So they are likely to be there in the cache, and the block that has lower priority would be more likely to get kicked out. Eviction is basically, what do I pick? Which one do I pick to evict from the cache? Kicking the data out, we call this eviction. Putting the data in, we call this insertion. The process of moving the new thing in and kick something out, we call this cache replacement, right? So when we look at this whole process, it means that there are certain policy. When the cache is full, when everything is full, you want to bring new data in, it means that you need to find something to get kicked out, right? And this is called replacement policy, and this is a design choice. This is what I said when I mentioned that, hey, me as a hardware designer, I need to figure out which one of these multiple policy is the best one for your program. A random policy is probably not a good idea, right? So how many of you write codes like this? Or I equals 0, I is less than n, plus ai equal b plus ci. How common is this kind of program? You iterate to array, right? And yeah, this is really common. So when I need to design a hardware and I need to design this caching policy, what I do, this is actually what computer architecture is like. Look at how we program and figure out, okay, what are the common elements of my program? And this is one of the most common. What is the piece of data that you need to use every single cycle here? What are the two variables that you need every single time? I'll give you one hint. You need n every single iteration. Right? What is the other variable that you need all the time? Yep, I. Right? You need both I and n all the time. Right? So with this program, you know that, okay, whatever data I is taking, you better put that in the cache. Right? Anyone agree with that? You better have both I and n in the cache because you need it all the time. Agree? All right. So our policy hopefully put I and n in the cache. What's next? Let's say this is 8 bytes, right? So if I have a 0 and my cache block is 64 bytes, if my cache block is 64 bytes, if I bring in a 0, what else am I bringing in? So A0 is the first 8 bytes in that 64 cache block, right? What is the second piece of 8 bytes in that 64 cache block? A of, what is the next number after 0? A of 1, right? Think of it this way. You have the cache block like this, right? This is your cache block, this whole thing. So when you bring in A0, the whole 64 bytes inside the cache block, you actually bring in A1, A2, A3, A4, A5, A6, and A7, right? You actually got A1, A2, A3, A4, A5, A6, A7. Are you still with me? Basically, because one cache block is 64 bytes, so when you want to access just A0, A0 is 8 bytes, right? You got the whole thing. You got this whole 64 bytes. Are you with me? Yes, no? If you're not with me, please say no so I can explain it again. Okay, again, please. Got it. You are with me that a cache block can have different sizes, right? It can have 32 bytes, it can have 64 bytes, depending on how I define how big my cache block is, right? So everyone's still with me with that, right? My cache block is this chunk of data. And then let's say A is a long integer, right? Long is an array of long integer. How big is that? Let's say it's 8 bytes. Let's say A of I is 8 bytes, right? So you're still with me, right? When I access these 8 bytes data, I go to the main memory, I go to DRAM, say, hey, get me A0. DRAM said, okay, I can actually give you this whole 32 or 64 bytes depending on how big is my cache block. So let's assume that it's 64 bytes. Let's assume that 64 bytes is my cache block size. So when I access A0, I get the entire cache block that A0 is in. Are you still with me? Basically, whatever data A0 is in, I get the entire cache block. So I access A0, I get the entire data around A0, that cache block. What would be my data around A0? If A0 start at the beginning with that cache block, right? It means that the other bytes become A1, A2, A3, A4, A5, A6, A7, right? Because it comes with that cache block. Are you following me? Okay, so basically what you got here is the entire cache block that you get. So let me set this real quick. So you get an entire cache block, right? So so the question is, if the cache block is 64 bytes and A of I is 8 bytes, you get A0 to A7. Don't forget that it starts from 0, so the number of things in that would end at 7, right? But basically, you get the entire block. There are a little bit of caveat here, depending on where A0 starts. Let's say A0 is in the middle of the cache block. You can get A0, A1, A2, A3, and then also whatever is before A0, right? Depending on how you align your data. I'll draw this during the in-class exercise. So I think this need more drawing, and I don't have room on the slides. So let me explain these corner case. It's actually not corner cases, but hopefully you get the idea. I want to access 8 bytes, but you get the entire 64 bytes. Right? What does this mean? The next iteration that I have A1 is already in the cache, right? Because I bring in 64 bytes. So are you all with me? Basically, the next, when I increment the value of I, A1 would be in the cache. B1 following the same logic. I mean, hopefully they are also in the cache. C1 is also in the cache. what is the next index? What is the next value of I that I have to go access my data again? Not A1. A1 is already in the cache when I access A0, right? Because I got the entire cache block, which means that when I want to access A0, you got A1, A2, A3, A4, A5, A6, A7. It's just because your data access is smaller than one cache block and the DRAM give you entire cache block. So what is the index? What is the value of I that would force me to go to the memory again? Yep, A8, right? Because you already have A0 to A7. So the next time you need to go to the main memory, that's A8. These two phenomenon, the fact that I and N like get used all the time. So this is probably the easier one. The value I and the value of N, you are going to use that data all the time, right? This is called temporal locality. What does it mean? Temporal locality means that I have an address, and there's a high chance that I'm going to use that address again. Are you with me? Basically, I have address, say, I here, the address of I. There's a really high chance that I'm gonna have come back and use I again. That is called temporal locality. This thing is called spatial locality. Spatial locality means that, let's say I access A0 because I got A1, A2, A3, A4, A5, A6, A7 with me. That's also because you write a program like this. It's likely that you are going to access whatever's next to you, right? The way to remember this is temporal is time, right? Spatial is space. Time means that in the future, I'm going to access the same address again. Spatial means space, means that in the future, even though I'm not accessing my own address, my neighbor address will be accessed. All right. So based on these two locality, one of the policy that get used the most often is called least recently used, or sometimes we call this LRU. This is used everywhere. Software cache, hardware cache, the L1 cache, L2 cache, page cache, most of the cache would try to imitate LRU. Why? Because it kind of makes sense. It's based on the concept of temporal and spatial locality. Right? As I said, the cache that hasn't been used in a while are not likely to be accessed. Let's say I declare a variable and then I go through the loop, I use I a lot. Like from the earlier example, I use I and N a lot until I exit that loop and I forget about it. I'm not going to use I again, right? That means that I can kick I and N out, right? So it basically LRUs is based on the fact that if I have not touched an address for a long time, it's probably safe to kick them out. Any questions about this policy? Basically, because I have not used these particular address for the longest time, it's probably safe to get rid of them. Are you with me about the definition of the policy? All right, so let me grab water real quick. So that's the idea. The idea is behind the fact that when you write a program, you have temporal and spatial locality. So the benefit is probably the most effective policy that you can get. It's actually really effective. But here's the downside. We are not going to question you about the downside on the exam for this class. It might appear in a computer architecture class, but basically a full-blown LRU can be hard to implement in hardware. Don't worry about that. Basically, if I say on the exam, okay, the cache use LRU policy, you know that, okay, I would have to keep a record of when do I last access each cache block. When new data comes in, I kick the one that is the oldest that I have not accessed in a long time. What can kill the LRU policy? This is called set thrashing. What is thrashing? Let's say you throw something into your garbage bin, right? What does thrashing mean? It means that someone digs in the trash out, right? And it's kind of spilled over everywhere. So thrashing means that when there are just too many data mapped to the same set, right? Let's go through this example. Let's say I have a four-way cache, right? Let's say I have the four-way cache, and my program go through cache block A, B, C, D, and E. All of them map to the same set. So this is one example. I have A, B, C, D in the beginning, right? The next time I access, because my access pattern is A, then B, then C, then D, then E. So the next access is to E. What would I do here? Which one am I kicking out? Remember, I access A, followed by B, followed by C, followed by D. So which one of this block is the oldest? A, right? So A is the oldest. So yeah, E kicks out A. What is my next access? I'm gonna loop through A, B, C, D, E, right? So now I access E. The next thing I'm accessing is what? A, because let's assume that I don't even have to access F. So I do this A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. So the next time I'm gonna access A. But do you see that now I just kick out A, right? I just kick out A. So when I access A, which one am I kicking out here? B, right? So A would come in, replace this. What is my next access? B, right? Because my access pattern is A, B, C, D, E on repeat. So next time I'm gonna access B. Which one am I kicking out? I kick out C. I replace C with B. Then the next access is C, right? C kicks out D. And then the next access becomes D, which will then kick out E. That was the last time I accessed. So D would replace this. Do you see that in this case, even though I have the cache, I never get to use them. It's all cache misses, right? With just this pattern, it's all cache misses. Are you with me? But basically, if I have four ways and I access A, B, C, D, E, and I make sure that A, B, C, D, E all map to the same cache set, I will never have a cache hit. Any questions about this, or are you with me? Like, do you want me to repeat this? Okay, so you're confused. So let me do it again. All right. Okay, so first of all, let me do another one that would keep track of cache misses, right? Oh, and number of misses, and then number of accesses. So the first access is to E. E kicks out A, right? So E kicks out A. You with me, right? So far. We kick out A. Is access to E a cache hit or a cache miss? It's miss, right? So let me keep counting. So the number above would be counting number of miss. The number below count number of accesses. Next access is to A replace B, right? Is this a miss or a hit? Also miss. right? So you access, and that access is a miss. Now B comes in, kick out C again, right? Cache miss because I want B. B is not there, and then B kicks out C. So I access again, and that access is miss again. I have C coming in that kicks D, right? Also miss again, right? You have access to C. C is not in a cache, so that's a cache miss. Go back to D. D kicks out E, right? Also miss. So if I have to access to do this, A followed by B, followed by C, followed by D, followed by E, comes back to A, then B, C, D, E, and then repeat from the beginning, I would have 100% cache misses, right? Are you with me? That basically, if you happen to have this pattern, if you write a program this way and it just happen to be that mapped to the same set, yes, that is a great question. If my access change from A, B, C, D, E, A, B, C, D, E into just A, B, C, D, and then repeat A, B, C, D, what is the cache hit rate? Do I ever have a cache miss? Actually, next question. If that's my access. Yeah, so I mean, yes, if someone use the cache and kick out something, but you will have some cache hits, right? And if A, B, C, D is the only thing you access, then you get 100%, right? So now you see that the way you write the program, the way you write your loop, even the way you write your loop can impact number of cache misses, right? And I mean, we can fix things in hardware a little bit. There are papers that, so this is definitely not going to be on exam. This part is definitely not on the exam. On the exam, the rest can be. The rest can be. So I can ask you the access pattern that would give me 0% cache hits, right? I'm not gonna ask you to go read the paper, but yeah, so we can design the cache and fix the hardware. That's one way you can improve the cache hit rate. Another way is you write the program knowing how cache works. With that, you can get close to 100%. And I'll give you some example in a bit. So, okay, so now we talk about replacement policy, right? To kick out. Let's talk about, okay, when we bring this new thing from DRAM, right? When cache miss happen, we get data from DRAM. These data will be put in the cache, right? Typically, we will just mark them as the most recently used, right? This is pretty trivial. Basically, we bring in new data. That data will mark them as the most recently used or MIU. Any questions? This part is really simple. Basically, when we put new thing in a cache, we would thought that, hey, we are probably going to use it again. Promotion policy is when I access something in the cache. It's not a new data from DRAM. Same logic. Most of the time, we just put them in the MIU. Actually, right now for this class, let's assume this is the case. And this can be done by updating the hardware. Not going to cover for this class. If you're interested, stay for computer architecture. So insertion and promotion policy, simple. If you access something, that becomes the most recently used cache block. They are least likely to be kicked out. That's it. So let's cover three types of cache misses. Right? There are fundamentally, if you look at every single program, there are three ways cache miss can happen. Compulsory miss. This is the first time I see this address, right? The first time I see this address, so I can't do anything. Data is obviously not in my cache. Any question about compulsory miss? Basically, it's the first time I see this address. There's no way I can bring them into the cache or not. Actually, there are techniques to do that. But yeah, most of the time, the data would have to be brought into the cache first. So that generate the first cache miss. And hopefully you get cache hit after. The next type of cache miss is the conflict miss. Right? The conflict miss is what I shown earlier when I have A, B, C, D, E. That exactly is what defines conflict miss. You go to the same cache set, so even though the other set is empty, because your access go to the same set, they kick each other out. The last type is capacity miss. You just don't have unlimited cache, right? So at some point, it's going to be too small to cache everything. The second sub-bullet are things that you can do both from the software point of view and the hardware point of view to improve cache performance. Just something to let you know, again, not going to be important for exam. For exam, just know that there are 3 types of cache misses. What does each of the types mean? So I've been talking about cache is fast, right? Way faster than main memory. So let's actually think about performance. The first performance measurement that you can do on whether my program is good or not, cache hit rate, right? You want to write a program that access data in the cache. Any questions about the cache hit rate and that they are good? You want more cache hits, basically. Any questions about that? The next thing that measure performance is what is the cost of each cache misses, right? Which kind of ties to the last thing. What is the cost of my data load, right? When I access L1 cache, it's probably really fast. But if I have a cache misses in L1 and then cache hit in L3, that's probably a little bit slower. So let's go through some examples to make sure this is more clear. Let's say L1 take 2 cycles, L2 take 5 cycles, DRAM take 55 cycles to access. And then my program issue 100 data load. When I go to L1, it hit 80% of the time. When I go to L2, it hit 80% of the time as well. How many cycles does all this 100 data load takes? I will go through this example so that I can show you how to work through this question, right? I have 100 loads, right? How many of them hit in the L1? What is 80% of 100? Yep, 80% goes to L1 and hit, right? 20 goes to L1 and miss. Okay, so how many data access would have to go to L2? 20. Yep. So this check L2. How many of them would go to L2 and hit? 16, correct. So 16 goes to L2 and this is a hit. 4 goes to L2 and this is a cache miss. Right? So how many ended up having to go to DRAM? 4. Okay. So 4 goes to, oops, DRAM. How many goes to L2? Close enough. Don't forget the 4 that missed. So 20, right? 20 goes to L2. Any questions why it's 20? Basically, you need to go to L2 to figure out, oh, it's a cache miss. So 20 of them still go to L2. All right. Are you with me that it's 20, not 16? Okay. So 4 of them go to DRAM because it's a L2 misses, right? When you need to check if it's a hit or a miss, you still need to access L2. You need to look up. Basically, you need to go and check, okay, what's my index bit? What's my tag bit? And let me look it up. So no matter whether it's a hit or a miss, the process of checking if it's a miss or a hit, you need to access L2. So 20 of them actually need to go to L2, right? Not 16. The other 4 that miss in L2 also go to L2 and then figure out, oh, okay, my data is not there. So they still need to check L2. How many need to go to L1 using the same logic? 100, right? So 100 goes to L1. How many cycles does it take to access for DRAM? Like for data from DRAM? 4 multiplied by 25, right? 100 cycles. How about this? 100 again, right? Because that's basically 20 multiplied by 5, right? Multiplied by 5. So 20 multiplied by 5. How many cycles do I have to spend to access L1? 200, right? So in total, to finish all these 100 loads, you spend 400 cycles. That's the final answer. Because 4 of them has to go to DRAM, that takes 25% of the total time, right? Then 20 of them go to L2. That's also 25% of the total time. The rest go to L1. So 400 cycle in total. What if every single one of these loads has to go to DRAM? How many cycles do I take? What if all 100 loads has to go to DRAM? That's 25 multiplied by 100, right? So that's 2500 cycle. So do you see that, hey, at least having the cache make this a lot faster, right? Everyone agree with me, right? That having the cache here is making this way more faster than not having the cache. Any questions? All right, so let's go through the next example. Almost the same setup, but now I have 1000 loads, but this is the hit rate. Tell me how many access to L1, how many access to L2, and how many access to DRAM. All right, so L1 accesses, yep, that's 1000. Okay, so how about L2? You hit 99% of the time. So what's, yep, 10, right? So it's 10, it's 1% of 1000 that has to access L2. How many DRAM accesses? Two. Okay, so how many cycles in total? Uh, yeah, 21 2100, I think. So this is 2000. This is 50, right? 5 multiplied by 10, and this is also 50. 25 multiplied by 2, that's 21,000 cycle, right? So you now notice, right? If I overblow number of memory access, even though I have a really, really good hit rate, the performance is not great. You still notice this, right? Even with a really good L1 hit rate, the performance is not great if I have to issue a lot of memory requests. How about this? I issue only 10 rows and I have a really crappy L1 and L2 accesses. So L1 accesses is 10, right? You have 10 loads. So they all have to go to L1. What's the number of L2 accesses? What is 50% of 10? 5, right? And then L3, how many? 3, right? 60% of 5 is 3. So in total, this is 95 cycles, right? A little bit faster, actually quite a lot faster with this. All right, so anyone want to pitch in some ideas about how can I make my program run faster? What can I do? What can I do? How can you decrease the load? That's why you study algorithm, actually. So if you study algorithm, there's a big O notation, right? So I hope this big O notation has been haunting you on those classes. This has the compute element and the memory element. Oh, am I wrong here? Okay, that's 75, right? And that's oh yeah, that's 25. Okay, that's already more than 100. My bad. So that's 120 cycle. Okay, thank you for your correction. I just trust you on doing math. Okay, so that's 120 cycle. But yeah, you have how much compute are you going to generate and how much memory, what's the size of memory that you are going to generate. So you can reduce the number of loads by using less memory, using less function calls, right? If you go back to assembly lecture, function calls access memory. Remember that? It goes to the stack, right? Function calls can increase number of memory accesses. Passing down a lot of variables also access the stack, right? So it increased number of DRAM accesses. So there are actually quite a lot of things you can do in the program to reduce number of loads. What else I can decrease? So yeah, obviously you can decrease number of loads. I can then increase, right? Increase the cache hit rate. If I increase the cache hit rate, then I go to the memory less often. So do you agree that given the same amount of load, if I have better cache hits, program is faster? Yes, 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 yes. Hopefully everyone said yes. Okay. Another thing, and also why I study architecture, I can make this smaller. So make this smaller. This is good. Make this higher, right? This is also good. I can also make this smaller. Yes, actually you can buy faster DRAM. DDR4 is faster than DDR3. Cache, different different generation of the cache has different speed as well, right? Anyone want to guess sometime why we talk about 7 nanometer versus 14 nanometers? Why is 7 nanometer faster? It's actually because they're smaller. So if let's say 14 nanometer is that big, right? So if you want to move electron from here to here, you need to cover that distance. Now you shrink the area smaller. Now electron has to cover less distance, and that can make things faster. You can come up with interesting design from hardware point of view that can increase the capacity of the cache. That can also increase the hit rate, right? So there are many things you can do here to make program faster. You can increase the capacity, you can increase the hit rate, you can decrease number of loads. Anyone want to guess why suddenly machine learning become useful? Oh, how can we decrease number of loads? Change the algorithm. Basically, you can change the algorithm so that when you compute different things, use register rather than data access. That's one way you can do that. The second way, call fewer functions. when you have the function calls, you remember our assembly lecture, the third one, right? Where you have a function calls, you need to save things to the stack, you need to save the variables and all those things. The stack is on DRAM. So if you have fewer function calls, you can have fewer loads. You can pass less number of things into the function, right? Remember the arguments into the function. The first 6 will be passed on to the register. Anything more than 6, that goes to the main memory. Okay, so those things can decrease number of loads. Okay, yeah, so hopefully when you write a program, be aware of the cache usage. There are multiple things you can do to improve program performance. And let's go back to my question. Why do anyone want to guess why suddenly machine learning becomes possible? So if you run machine learning workload, one thing that you would realize is it uses so much memory, use so much cache. Right? The fact that hardware gets a lot better, it's the only reason why machine learning see the light of day these days, and it still demands so much hardware. So I want to, I guess, claim that it's not just pushed toward machine learning, but also it's pushed toward every single direction in computer science that kind of make all the program better. You need to change the algorithm, right? That would increase the hit rate. That would decrease number of loads. You need to change the hardware. Now you have bigger cache, bigger DRAM, faster DRAM. You need to actually push the program, change how you compute in the machine learning, and now you have deep learning, which can be really powerful. So to reduce the miss rate, right? As I said earlier, there's so many ants on my laptop. Sorry. Uh, so when you're looping, right, when you're looping over a large range of data, make it cache friendly. Make sure that you don't do that thing where you have A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. try to figure out if I want to shrink that a little bit, right? We'll go through some of that example on the in-class exercise on Wednesday. Another thing you can do is remember that one cache block is multiple words, right? As I said earlier, if I access A0, you got A1, A2, A3, A4, A5, A6, A7. So be aware of that. You can reduce number of memory access. I talk about this for 3 times now, right? So you probably got it. And then now you might have used a bunch of modern libraries and APIs, right? That somehow make your program faster. I can tell you one of the main thing that this API is trying to do. Optimize for cache locality. That's why they get the performance from. This is one of the major source of performance gain. If you want to somehow in the future go work on certain jobs and want to come up with good APIs, these are some of the things you can follow. Check the machine's cache size. You can actually check it. Each processor, they will tell you what's the size of the cache, what's my associativity, so that you don't have the case that you go through A, B, C, D, E, you will then go to A, B, C, D, A, B, C, D, A, B, C, D, right? Then you get 100% hit rate. Make sure the program rarely need data from DRAM because that's slow. You can prefetch, you can do divide and conquer. These seems like unknown topic. These slides is for your information. It won't go into your exam. One thing I want to tell you is cache hits really matter. Like cache hit really matters. I'll skip this part for now. We'll continue on Wednesday. But whatever I'm gonna talk about next would be kind of like a primer toward the computer architecture, and I hope this is the new content that your senior or people who are from the 59 and 60 class, actually they never know about this, or if they know, they probably forgot about it. So these are some of the things that I'm gonna tell you and hopefully motivate you that, hey, hardware can, if you know hardware, you can do cool things on it. Or you can go full blown on my direction, which is come up with new hardware. And hopefully you find these things maybe a little bit interesting. Right, so let me skip to the end, which is exam. All right, so before we leave today, now it's 3:10. I want to kind of switch over to the in-class exercise. But before that, let's talk about exam. And here is the breakdown. I anonymize everything here. So hopefully no one has issues that I show this breakdown. A few things I want to tell you, right? First of all, there are people who did really well, like implement a pretty good version of skipless as well as the maze solver. As you can see here, every single one of you get more grade after curve, right? So no one get the same grade. Anything below, anything above the blue line, anything above the blue line is essentially your extra credit, right? The original extra credit is 10 points. Now with the curve, you get 20 points. This curve also, if you ended up answering only the first question, which is the Linux question, you still not miserably fail. You can still get a passing grade. You can even get a pretty decent grade, right? Think about it. This is 20% of your grade. So if you get something like 35 to 40%, right? That translates to about 7 out of 20. You only lose 13 points for now. If you somehow get full credit on the rest, you get, I think, a B plus, right? And remember that I'm still going to curve the final exam as well. Not sure how, but it would be the same. Basically, I would make sure that once I curve it, it has this distribution. And the distribution that I found is like you either try all the questions and then you get more than 80. Like for people who get more than 80, folks who try all the questions and they did the decent jobs on most of the required ones, right? How to process the files, how to get the queue implemented. Those two are really basic. You need to be able to do that before the midterm. The assignment tool already asks you to do it. Implement some form of searching and insertion. Not many of you got it correctly. You doesn't really ended up using the tool level. You get like points docked off a little bit, but then at the end of the day, with those alone, you don't even need to full blown fix and complete breadth first search. You'll be at around 70 to 80. And after the curve, if you're at 70 to 80, that's close to 100 already. People who got around 60 or lower basically doesn't really submit one of the programming question, right? This is basically the room where you can still get a really good grade. And I really encourage you to try. Don't look at this, oh, okay, I'm not gonna pass the class or like not getting good grade. If you submit all the assignments, if you submit all the in-class assignments, and you do okay on the final exam, I'm sure you do well. Right? Please do that. People who got around 37.5, which is 30 curve, right? You did not submit anything on the C code. I can't give you anything. Okay, that's a great question. When you submit the in-class exercise, don't worry about them being incorrect. As I said, those are your sandbox. So yeah, so the grade, originally, if you read the instruction, it's supposed to be out of 100. My curve is, instead of out of 100, it's out of 80. Anything above 80 becomes extra credit. So whatever grade you saw on Canvas, that's already curved. My comments, I would say original X over Y. The Y is 80. That X is your original grade. All right. So if you did not submit the C code, there's no way I can give you any grade on the C exercises. This is unfair for your peers, right? For people who actually try and implement and spend those 24 hours trying to get something submitted, right? You can not study going into the exam and expect that you get good grade. It's just impossible. You can't unless you have black magic, which in that case, feel free to use them. Why the curve? I think basically here's the curve. Anything above 80 is extra credit. Conversion rate is 50% per point. Those of you who get more than 100, awesome. I really love your solution, and you get tons of extra credit. After curve, you get more points. Those of you who miserably fail, still chance to pass this class. I'm not gonna murder you on that, right? Even though I'm upset that you did not even try to do anything on the C code. Where will extra credit go to? Whenever you lose point, I mean, at the end of the day, your maximum point is 100, but then this extra credit would be distributed based on whatever point lost, right? It would go to the total grade. These extra credit give you more room that you can make mistakes in the future exams or assignments. Take it as my reward for trying hard, right? Yeah. So this my curve hopefully give you a chance, like a solid chance. To be honest, if you submit all the assignment and in-class exercise, I'm sure you'll pass. So this gives you a solid chance to pass this class, but it doesn't reward those who do not try, right? And those who are in the middle can still recover and still get an A. with this curve, I can still make sure. Like basically, it's possible that you get an A out of this class, right? There are still 2 more programming assignments, tons more in-class exercise, and you can still recover in the final. And you can expect the same thing. Final will be like, there's some extra credit on that as well. Okay, so let me talk to you. Let me talk to you during office hours because I think you got confused. Basically, this is the grade. After curve, everyone should get more points. And the way I put it on Canvas, I'll double check that, but you should get more points. Actually, let me check your grade right now. At least on my Excel spreadsheet, everyone get more points because I apply the formula. Your actual grade is also 100. Yep. Yep. So at the end of the day, it's out of 100 for the actual grade. I curve it back to 80. Otherwise everyone fail miserably, except for a few people. So that's the curve. And your grade on Canvas, if you click on grade, that's already been curved. All right. So going forward, I want to mention there's still a lot of chance to recover your grade. There's assignment 3 and 4, and hopefully they're fun. Don't forget to submit your in-class exercise. I feel bad when you don't submit because I want to give you points. If you don't understand, ask as soon as possible. That's why today I leave a lot of space. So like, if you did not catch up, let me know right now so I can repeat what I'm trying to explain. I've been telling actually some of you during office hour that, hey, I know online classes is not perfect. I can't see your face. If I'm in the same room giving lecture, I can see the face where the students get puzzled, right? Now I cannot. So the only way I can tell that, hey, I need to slow down or I can speed up is you interacting with me through the chat. If you feel like you don't want to send a message to everyone, send me the private message. I would try to repeat the question. Basically, if you send me a private message, I will repeat the question so that all your friends know the question but don't know who is asking. And then I'm going to cover that. This is hopefully it's a more effective way to get everything to explain everything. So ask as soon as possible, take advantage of office hour. Many of you probably realize by now that you can actually request for extra office hour just by sending me emails. I'll find spare time and be there on Discord. Okay, so now in class exercise 9, go to the PDF. I would end this lecture and then move over to Discord because I feel like that's a better way to have everyone talking to each other. At least it seems more fun that way. Yes, so the question is you can still submit in class exercise until the last day of class, Make sure you submit it before the last day of class. Just in case OAA tells me, okay, you need to submit by this day. The last day of class is probably safe as the last day you can submit the in-class exercise. All right. Yeah. So basically, this is basically the latest I can do so that OAA doesn't yell at me. I'm like, why? Where's the grade? Right. So yeah. Let me save everything and move over to Discord. So that's it for the lecture today. We'll switch over to Discord. I mean, while I'm switching over, you can ask question right now. That's also fine. Okay, so let me know. Send me the zip file. That's fine. I'll regrade. If you zip and it just turned out to be an empty folder, that's why I was puzzled when I'm grading your question because there's nothing in there. Okay, so about cache hit and miss. Okay, yes. What's the question about cache hit and miss? Oh, the second, yeah, it's still a hit because if you go through that example, because nothing kick the old elements out. So if you do A B C D A D A B C C C C D D D, everything would be hit. Basically, you kind of need to go through what are the address you're going to access. Is it a new content? If it's a new content, do you kick the old thing out? If you're not kicking anything out, it's a the whatever is in the cache is going to be the same thing.